Hello everyone, welcome to this online course on material science. This is lecture 17 in module 1 on magnetism. If you recall, in the last lecture I have mentioned that to understand paramagnetism in a quantum mechanical setup, you really need to understand three different types of angular momentums, right? And those are denoted by the orbital angular momentum of the electron, the spin angular momentum of the electron, and then the total angular momentum of the electron, right, denoted by J. In this lecture I will discuss about the first one. So let me start about this orbital angular momentum, right? So let's try to understand how you define orbital angular momentum in classical physics, right? So you define it as a cross product between the position vector and the momentum of the particle, right? Each of these are vector in 3 dimensions because we live in 3 dimensions. So how do you define this quantity? Let's say we have to evaluate the determinant, right? And let's say we have Ix along the x-axis, Jy along y-axis, and Kz along k-axis, 3 unit vectors. And for R we have 3 position x, y, and z. For P we have px, then py, and pz, right? And how do you write these things out? So the x component of the angular momentum is now ypz minus zpy, right? So ypz minus zpy. The y component of the angular momentum can be written as xpz minus zpy. Let me make it a plus so that I can write it as zpx minus xpz, right? And then we have the z component, which is the kz. Sorry, that should be a jy, and that's a kz. It's like xpy minus ypx, right? So these are the 3 components of the angular momentum, and let me denote them by Lx, Ly, and Lz, right? So when we elevate these things in operator mode in quantum mechanics, we need to put the hats, right? So now I am operating in quantum mechanics by putting some hats on every x and every p, right? So all of them are now operators, and you have to be careful about their ordering. So this is Lx, Ly, and Lz. Every component now becomes an operator. So the next thing you need to know about this operator is that what about the commutation, right? And you remember what is this commutation is defined. So the commutation between the Lx and Ly, we need to know what is the commutation between Ly with Lz, right? And then what is Lz with Lx, right? So this is IH times, so here we have Lx and Ly. So on the right hand side we will have the third one. Here we have y and z, so on the right hand side we will have IH bar times Lx, and here we have z and x, so it should be IH Ly, right? So the primary point to note here is that none of this commutator is 0, right? So the individual components of the angular momentum do not commute with each other. That's the central point. You should remember always that they are the individual components do not commute. So as a result, we cannot have simultaneous eigenvectors for every one of them, right? So when 2 operators do not commute, one of the meaning is that they do not have, or they do not share, a common set of eigenstate, right? So then the question is, how do we find a set of commuting observable or set of commuting operators? So this is really important, because then if the operators commute with each other, they will have a common set of eigenstate, right? That's really an important issue. So in that search, I will give you the rule is that when you define an operator by forming a dot product between L, which is nothing but the L square operator, right? This operator has interesting property in a sense that although these components do not commute with each other, but you can take it as a rule that this L square operator commutes with every components of the L, right? That's 0. And what this I index subscript here can be X, it can be Y, it can be Z. So Lx commits with L square, Ly commits with L square, Lz commits with L square, right? So that's why this operator is very important, because this operator commits with every component of the angular momentum. Take it as a rule. I'm not showing you how this becomes 0, but take it as a rule. Now the next thing to understand is that usually among x, y, z, we apply magnetic field in some direction in the problem of magnetism, right? And the canonical direction is the z direction. That's why we usually talk about Lz. So among x, y, and z, we always prefer the direction Lz, right? So that's our starting point of for the angular momentum, orbital angular momentum. So when they are commuting with each other, it means that they have they share, that's the important message, they share a common eigenstate. We will see what that state is, but let's try to understand first. The commuting two operators L square and Lz share a common eigenstate. Now the question is, how do you label this eigenstate, right? So what is the eigenstate here? Usually in the standard textbook, this is a state, and you know that in quantum mechanics the state must be a ket vector, right? So in the standard textbook, it's denoted by a ket vector, but with two levels. One is L, another one is M subscript L. You remember this, right? So two subscript we need. And L, this level is something to do with the total angular momentum operator, and this ML is to do with the Z component of the angular momentum, right? And we will see how they operate with each other. So ML is, and then this L and ML, these are called the quantum numbers, right? These labels, quantum numbers. And L is the quantum number associated with the operator L, and ML is the quantum number associated with the operator Lz, right? Now we need to know how this state is acted upon by our operators, right? So which two operators is our choice? One is L square and another one is Lz. So let's try to understand how L square operates on this state, right? And we said before that this is an eigenstate. So what is the purpose of the eigenstate of some operator? So that's an operator. It's operating on some eigenstate. It means for sure the state on the left will be the same, right? Because that's an eigenstate of the operator. When it hits the state, it will give you the same states for sure. But we will have some eigenvalues, right, in front of the state. And let me give you the eigenvalue here. And this is L, which is the L quantum number, L into L plus 1 times h bar square. You remember, one thing you should always remember is that angular momentum has units in h bar, right? So this is L square, and these are unitless numbers. L is a 1, 2, so unitless number. So this is the h square is the unit of the angular momentum square, right? That's why you have to have a h square here. So that's the eigenvalue of the operator L square in the state LML, right? You remember this expression is very important. Okay, and the second expression is that about this LZ. So the Z component of the orbital angular momentum when operates on this state, it produces this number ml times h. So this LZ doesn't care about L. It hits the state and give you this number, the ml quantum number, times the angular momentum unit, which is h bar, and then the same state. So from these two equations, the conclusion is that LML, this state, is an eigenstate of L square and LZ. So L square and LZ share a common set of eigenstate, right? And why? Because we know they commute with each other. That's the central message. That's why people look for commuting observables so that you can form a common set of eigenstate, right? And whenever you see states like these, LML, you have to understand that the operator we are indicating is either the L or the L square or the LZ, right? And this important understanding of angular momentum will help us to evaluate certain expectation values. Let's say you will be given to find out the expectation value of this operator, right, LZ. Now we are trying to find out some expectation value. And you know from our previous discussion that whenever you want to find some expectation value, you need to know which state you are talking about, right? And you understand when you want to evaluate LZ, the state, because we need to put this operator between a bra and the ket, right? And you understand what should be the bra and the ket. It should be LML right now because they are the eigenstate of the LZ operator. So when LZ operates on LML, what you get? Let me write it here. So LZ on LML will give you ML times the H bar times the same state, right? ML. So that's just a number. You can bring it out of this expectation value. So we have ML and H, and then we left the bra and the inner product between the bra and the ket, right? And that's the same ket. And you remember the condition of the orthonormality. These states are orthonormal. It means when the bras and kets are equal, that's 1. So the result is ML times H, right? That's the expectation value of the operator LZ in the state LML, right? Okay. Similarly, you can evaluate this expectation value in different state. Let's say on the left we have some L prime, ML prime bra, and then we have LZ, but the ket is L ML, right? That's another expectation value. Now we are trying to understand, can we make a transition from this state to this state using LZ, right? And how do you calculate this expectation value? It's simple, right? So what happens when LZ operates on LML? So when LZ operates on LML, you will have MLH times the states, same state, right? And this number, you can bring it out, the same strategy every time. Now we have the inner product between L prime, ML prime, and L, ML prime. And the condition of the orthonormality suggests that in order to get non-zero value, the L prime has to be equal to L, and ML prime has to equal to ML. Sorry, there shouldn't be any prime here. So, and how do we enforce this condition of the orthonormality? You say the chronicle delta that L must be equal to L prime and M prime must be equal to M, right? That's how you evaluate the expectation value of the LG in different state, LML and L prime, ML prime. And With this, now let me find out the expectation value of the L square operator, right? Let's say we are trying to find out what is this. So what is the state here? State is LML, L square, L, ML, right? And you know what LML, L square will give you when operates on LML, right? So let me write that first, which is L times L plus 1 H square times the same state, right? LML. So that's just a number. You can bring it out. L plus 1 H square L ML, right? So that's the value, and we have the inner product. Sorry, that should be a bra. Let me write this line again. So when I bring this number out, L plus 1 H square, then we will have the inner product between LML and LML, right? So that's one orthonormality condition. So the result is L into L plus 1 H square, right? That's the expectation value of the L square operator. And similarly, here we have find out the expectation value between two same state, right? But somebody can say, okay, what about if you want to calculate the state with let's say L prime and ML prime, right? And then L and ML, so two different states. How do you do that? So L prime, ML prime, and then L square, LML, right? Now you know how these things operate. So that's L prime, ML prime, and here we have L plus 1 H square LML, right? And that's just a number. You can bring it out. So L plus 1 H square, and here you have L prime, ML prime, L, ML, and you again impose the orthonormality condition, which says that L prime has to be equal to L and ML prime has to equal to ML, otherwise this thing will be 0. So that's why you enforce this condition by 2 Kronecker delta. You say the delta L prime, so L has to be L prime, and also delta ML prime ML. So ML prime has to be equal to ML, otherwise you will get a 0 contribution, right? And that's how we usually calculate this expectation value of the orbital angular momentum and its squared value, right? And one important thing about this eigenvalues, right? If you see, when I would say LZ operates on this vector, you will get ML times H. When L square is operating on the state, you will get L plus 1 H square, right? There is a condition to be fulfilled for this ML, the quantum numbers ML and L, right? So let me illustrate what that condition is really all about. So the ML has a range between minus L to plus L in the units of steps of 1. So let's say we have L equals to, let's say 2, that's a number, right? What will be the ML? ML will be, starts from minus L, right? So minus 2, then minus 1, 0, 1 and 2. So how many value we have here? We have 5. So usually if you extend ML from minus L to plus L, you always have twice L plus 1 numbers of ML values, right? Here L is equal to 2, which is twice 2 into 2 plus 1 is 5. That's why we have 5 states, right? So for a single value of L, we have 5 different states with different MLs. Now the question to ask is that, how do we write this state? For example, let's say we have 5 states, right? So let me write one top of each other. So for every state here, the L is 2. So I'm writing L and ML, right? The Ket notation. So L is 2 always, but M can be, let's say, 2 first, the maximum. L is 2, then it could be, sorry, 1, then 2, 0, 2, minus 1, and then 2 plus, minus 2, right? So we have 5 of these states. You can think of these states one top of each other, right? Forming a ladder. It's kind of ladder, right? You can step up to the ladder, and you can step down, downwards in the ladder, right? And the question usually one asks that, how do we get up in the ladder, or how do we get down in the ladder, right? There should be a way to go from this state to this state, where L is fixed, but you increase the ML by some unity, right? And here it's always changing by amount 1. So what is that operator which will give you this stepping between the ladder? Then you need another 2 operator, which is denoted by L plus, right? The plus denoting that this will help you to go upwards in the ladder, and another one is the L minus, and this will help you to go downwards in the ladder, right? So let's say we are sitting in this step, right? And if I hit this step with this operator, this will produce this one. But when sitting here, if I operate with L minus, I will go down in the ladder, right? That's what these 2 operators does. And how do you define the eigenstate, or sorry, how do you define the operation of these 2 important ladder operators? So these are usually known as ladder operators. Ladder operators, and they will give, and now let us define how they operate. So our state is L ML, right? And we are operating by ML, LML. You know what it operator does, right? This one will increase ML by 1. So the state will be L remains the same, but the value of ML will be increased by 1. That's the state, but we have some values, right, associated with this operation, and this is given by, here I will have h bar root over L minus M, right, L minus LM times, everything is under root over L ML, then another bracket L plus M plus 1. That's how this L plus operator operates on the state. And for the L minus, let's say we have the state LML, for sure we know this will bring the ML 1 down, right? So it will be L, but ML minus 1, but the value is L plus ML. Take this as a rule, don't worry how to derive them, but take them as a given rule for calculation. And now one important point I want to mention before I end this lecture is that, let's say you are sitting somewhere here, right? The ladder, that's the highest step of the ladder, and then you want to go 1 step above, right? But there is no step above. So that's why when the state is in such a place where ML is the maximum L, and you want to operate with L plus, right, it will kill the state. Similarly, when you're in the lowest step on the ladder, and if you want to go below this step, but there is no state below that, right? So if you hit L minus on this state, it will produce a 0, right? So this condition usually denoted by that when ML is already L, that's the maximum value of the L, right? It will give you 0, and also when ML is minus L and you are trying to go 1 step below, it will kill the step, because there is no state above this state and there is no state below this state, right? Okay, and the last thing I want to show you is that how do you find out the expectation value, right? Because I always told you, once you have some operator, the immediate thing you want to ask yourself is how do you calculate the expectation value, right? So I will show you the L plus 1, and feel free as take as a homework to perform the L minus. So I want to calculate the expectation value of L plus, and how do we do that? So the state is LML here, and you want them to be different. So this one is LML prime, and inside we have L plus, and this one is LML, right? What this state will give you, that will give you H times square root L minus ML L plus ML plus 1, right, times the state. And you can see that's just a number. You can bring it out. So if you bring it out, you will have L ML L plus ML plus 1, and then the inner product between, oh sorry, so I think I have made a mistake here. So it should be ML plus 1, right? Because this operator, when it hits on the state, it will increase the ML by 1, so ML plus 1. So now we need the inner product between ML prime, and here we have ML plus 1, right? And the orthonormality conditions dictates that L prime has to be equal to L, and ML prime has to be equal to ML plus 1. Otherwise, this is 0, right? So, and how do you impose that condition? So this is the same LML, L plus ML plus 1. Now you use two function, right? Two Kronecker deltas. You say that L prime has to be equal to L, and also the ML has to be equal ML plus 1, right? That's the expectation value of this L plus. And you will see if you use the L minus, there will be some sign changes, but the logic is the same. Take it as a homework, and the result for the L minus will be, you will have a plus here, you will have a minus here, and the rest will be the same. Take it as a homework and feel free to justify this answer, right? I think that's about the orbital angular momentum of the electron. If you understand what I have mentioned so far and then do some practice, I believe that that's about it. You don't have to understand anything more about this L regarding the paramagnetic problem. So and in the next lecture, my plan is to give you a self-contained introduction to the spin orbital angular momentum of the electron, right? For this lecture, that's about it, and thanks for listening.